Hello and welcome back to the course in algorithms. In this video and the next couple of videos, we are going to discuss what are known as greedy algorithms. Greedy algorithms are algorithmic techniques to solve optimization problems in which the greedy algorithms always tries to pick the best possible solution at this point of time, hoping that globally that is going to be the optimum solution. So the most of the time this trick doesn't work, and when it doesn't work we can't do much about it. If you have to show that an algorithm doesn't work, then you have to just give one example to show that it doesn't work. But when the greedy algorithm works, good thing about the greedy algorithms that it looks very simple to explain, it's very simple to implement. But the harder part generally is going to be proving that the greedy algorithm is actually correct. In this video and in the next set of videos, we are going to focus on how to prove greedy algorithms work correctly when they actually give you the optimum solution, right? In this video we will see a specific example. The example that we are going to consider is in the context of machine scheduling. You're given a collection of jobs. Each job has a starting time and ending time. You need a machine, and this machine can only process one job at a time, and you want to know among the given collection of jobs what is the maximum number of jobs that can be scheduled on one machine. This also can be thought of as a real life application where you have a seminar room in which you have to schedule several seminars. Each seminar has a starting time and ending time. At any point of time you can only schedule one seminar at a time. If you are scheduling, if some seminar is happening right now, you cannot start another seminar before the current seminar actually ends. With these conditions, given a collection of seminars with the starting time and the ending time, and you want to design a greedy algorithm to schedule the maximum number of seminars on one seminar room. We will see several greedy algorithms. Most of them don't work. When it doesn't work, so what all that you need to do is to give a counter example and say that this greedy algorithm fails to compute the optimum. But as I mentioned earlier, if one of them work, then we will try to formally prove that the one which works is actually is optimum. We need a mathematically formal proof. We'll try to do that in this video. So in this video we are going to study about greedy algorithms. Let's look at so what are greedy algorithms. Greedy algorithm is an algorithmic technique to solve optimization problems. It always makes the choice that looks best at the moment, right? The making and it makes a locally optimal choice in the hope that this choice will lead to a globally optimum solution. So it may not work all the time, but when it works, the algorithms will look very easy to understand, and also write the code for the algorithm. So what is difficult is that proving that why the greedy algorithms works when it works, and we will also say that this trick will not work all the times, and so in the case when it doesn't work, then we can't do much. But if you have to show that a greedy algorithm is not optimum, then we have to give a counter example to show that it's not optimum. But when the greedy is optimum, the main focus of this lecture will be to show formally that the greedy actually gives you the optimum solution. Let's start with a simpler example, specific example. We are given a set of jobs which has a start time and end time, and you are given a machine on which it has to be scheduled. So we have to find a schedule which with the objective that it will maximize the number of jobs that can be scheduled on this machine without a overlap. That means that at any point of time only one job can be there executed on a machine. So if two jobs are overlapping, then both the jobs cannot be scheduled on the same machine at the same time. So we want to find what is the maximum number of jobs that can be scheduled on one machine. so that all the scheduled jobs cannot conflict. Another real life example could be that let's say that you have a seminar hall, and there are several requests to conduct the seminars. Each seminar has a starting time and ending time. Once you decided to start a seminar, till the seminar ends, you cannot start another seminar. With this condition, given a set of seminars that needs to be scheduled, our objective is to find what is the maximum number of seminars that can be scheduled on the seminar room. Coming back to the machine scheduling problem, you are given a collection of jobs. Each job is associated with a closed interval. It has a starting time and an ending time. It has to be processed only during that interval, right? So, and we want to know what is the maximum number of jobs that can be scheduled if you are given only one machine, with the condition that you cannot schedule more than one job at any point of time. Let's look at a greedy technique here. Is there an optimum greedy schedule which includes the first job picked by the greedy algorithm? What do we mean by that? Greedy algorithm will pick one of the jobs which I call it as the first job and include in the solution, and since this job has been picked to schedule on the machine, any job which overlaps with this particular job cannot be scheduled along with this job. So once you pick one job, you have to delete all the jobs which actually overlaps with this job, because none of them can be scheduled along with this. So now you pick the first job, remove all the jobs which conflict with this particular job that you picked, and apply the same algorithm on the set of jobs that have not been picked, right? So the hope is that this is the greedy algorithm. So the hope is that at the end we will have the optimum solution. So now if I have to describe a particular greedy algorithm, then I have to tell you which is the first job to pick. If I are given a collection of jobs, which is the first one that I should pick, so that I discard all the jobs which conflict with that and apply the same algorithm on the set of jobs that have not been deleted. Let's look at the first candidate. The first natural thing is to do the shortest job first, because when I pick the shortest job, in a sense I want to delete minimum number of elements which actually conflicts with that. So it may be natural to think of the shortest job first to be the solution. So shortest job means that it is the time interval to which the job needs the processing, that is the end time minus the starting time, right? Since it requires very small amount of processing, probably they should be given the first priority. Here is an example where this is not the right choice. This will not give you the optimum solution. So first, if you pick this solution, so this diagram is such that this job starts here and requires time till here, and the next job starts here and ends here, and the third job need to be scheduled starting here and ending here. According to the shortest job first, this job will be picked. But if you pick this job, both the remaining jobs will be removed, and both of them cannot be scheduled along with this job. Okay, so but the optimum solution will pick this particular job, and so once this particular job is picked, you can't pick this job. So and it can also pick this particular job. The optimum solution will pick two jobs, the bottom two jobs, but the greedy algorithm, which picks the shortest job first, can only pick one job. So the greedy algorithm, which picks the shortest job first, is not optimum. Let's consider the first come first serve, right? So you sort the jobs based on their starting time, and whichever comes first, you can process that job. So but unfortunately this also will not give you the optimum solution, because there may be a request which needs to be which starts very early, but this is a very long job. If you start this activity, it will continue till the evening. But there are several other jobs which may not be the first one to come, but they come a little bit later than the first one which has come. But in that case, it will just require small amount of processing, The greedy will pick the bottom job, but the optimum is you can pick all these jobs. So this example shows that if you schedule the jobs based on first come first serve, this schedule will not be optimum. The next option could be you among all the jobs you consider the one which has the fewest number of conflicts, because the algorithm says that you pick one job, and once you pick the job you remove all the jobs which conflicts with that. In some sense we want to remove minimum number of jobs, because in the next iteration we are going to work with a larger set of jobs, so that hopefully we will have maximum number of job schedule on it. This example shows that this is also not optimum. In this example what you see is that this is the job which has the minimum number of conflicts, but the moment you pick this particular job you cannot pick the moment you pick this particular job you cannot pick this job because this overlaps with this, and you cannot also pick this because this overlaps with this. From now onwards in the next iteration you can pick one of these jobs and one of the jobs on the right hand side, right? So the total number of jobs that you can pick after you pick the this middle job is which has the fewest number of conflicts. You can pick two more jobs, so you can schedule at most 3 jobs. But you see that the optimum solution is 4, because if you schedule the bottom 4 jobs they will not conflict. So the optimum is 4, but the greedy algorithm which picks the fewest number of conflicts can only schedule 3 jobs. Okay, so even the fewest number of conflicts, the greedy algorithm based on that is not optimum. Let's consider the first to finish algorithms. In this case, instead of we will sort the jobs in the increasing order of their finish time. We look at all the jobs and pick the job which can finish first, right? So that is the job which we are going to schedule it, and remove all the jobs which conflict with that. And again among the remaining jobs we just look at the job which can finish first, right? So in other words, we sort all the jobs in the increasing order based on the finished jobs, and consider these jobs in the sorted sequence, and schedule the first job, remove all the jobs which conflicts with that, and again among all the unscheduled jobs pick the one which finishes first, and so on. For all the examples that we have seen considered so far, let's say in this example, so this job is the one which will finish first, so we'll pick this. So next we cannot schedule this because this conflict with that, so then you'll pick the bottom one, right? So in this case if you choose the first to finish, this will schedule the bottom 2 jobs, which is the optimum solution. Even in the example, so it will pick this one because this is the first one to finish, and second one they will pick this, and it will all pick the top jobs, so which is the number of jobs in this case will in this example you see that will be equal to the maximum. Even in this case the first job it will finish is this, so it will pick this job. Next it will delete all these jobs because it's conflict with this. The next job that finishes first is this, right? And you remove this job because this conflict with the job that I just picked, and then you pick this job, and then remove all these jobs because it overlaps with this, and then you pick this job, right? So in this case also you can see that if you pick the jobs based on the finish times you get the optimum, right? So for all the examples that you have seen, this algorithm which fix the first to finish seems to be giving the correct answer. But as I mentioned earlier, if you had to show that a greedy algorithm fails to give an optimum solution, one example where the greedy algorithm picks less number of jobs than what is optimally possible, that should be good enough. But if you have to show that a greedy algorithm actually computes the optimum solution, then we have to formally prove that that is the case, right? So we cannot give example and show that a greedy algorithm is optimum. Let's try to show this by contradiction. Let's define GT be the number of jobs finished by the greedy algorithm by the time t, right? So for contradiction, at the end of the algorithm, let's assume that greedy doesn't pick the maximum number of jobs. So let optimum be the optimum schedule which picks more number of jobs than what greedy can schedule. So since optimum schedules more number of jobs than the greedy, then there will be some time, let's call it as t dash, where the number of jobs scheduled by the greedy algorithm is greater than g of optimum solution is greater than the corresponding solution of the greedy, right? So what we do is that we have two solutions. The way to visualize is that we have the optimum solution, it schedules few jobs, right? So and we have a greedy solution which keeps scheduling some jobs in this particular manner. So at time t I count the number of jobs completed by the optimum, which is given by opt of t, and g of t is that when you take this job, what is the number of jobs completed by the greedy algorithm, right? G of t0 is the number of jobs completed by the greedy algorithm, already scheduled and finished. So now let's say that since the optimum actually schedules more number of jobs than the greedy algorithm, at some point of time, let's say this is the time, right? So this is the time. So this is the solutions corresponding to the optimum, and this is the bottom one is the solution corresponding to the greedy. This is the time t0 where the optimum, the number of jobs completed by the optimum is strictly greater than the number of jobs completed by the greedy algorithm. If the greedy algorithm, if there exists an optimum algorithm which schedules more number of jobs than the greedy algorithm, then there should be a time t0 where the optimum actually schedules more number of jobs than the greedy algorithm. T0 is the first time where such a thing happens. Since so to give an analogy, so you can draw the curve, right? So this is the time and this is the number of jobs completed by the greedy algorithm, right? So let's say that the graph could look something like this. So and what we are saying is that the optimum, if it has to do more number of jobs than the greedy algorithm, then at some point of time the number of jobs done by the greedy algorithm optimum should be greater than the greedy algorithm. This is the time that we are referring to as t0, right? So the first curve, this curve that I am drawing here refers to the optimum solution, and the original one that I wrote is for the greedy algorithm. That is the number of jobs completed by the greedy algorithm. So now let's look at this point of time. This is the first time when the optimum is doing more jobs than the greedy algorithm. So optimum should be completing a job and the greedy is still doing some job, because we only count the number of jobs which have been completed, right? So if both of them complete the same job at t0, then the count for both of them will go up by 1. So that's not the case, right? So greedy is more than the optimum, optimum is more than the greedy, and this is happening for the first time. That means that the optimum is finishing a job, but whereas greedy is still doing a job. Okay, so we want to understand what is the last job that the greedy has done, right? So greedy is doing something now, but we are more interested in looking at what is the last job that the greedy has finished. We want to ask the question whether the last job that greedy finished is actually after, this is the optimum solution, right? So this is our t0, whether this finished after this, right, after the starting time of this particular job, or this actually finished. There are only two cases, right? When you consider the greedy solution, the last job that the greedy finished either ended after the starting position of this particular job that is under consideration, or it ended before, right? We will show that both the conditions cannot happen, right? Let's say that if this is the case, if the job has gone up here, so during this entire period till t0, the number of jobs finished by the greedy is same, because it's not finishing any number of jobs finished by the optimum is same because it's not completing any job. But at this point of time, the number of jobs finished by the greedy algorithm increases by 1. But just before T0, T0 is the first time when the optimum is doing more jobs than the greedy algorithm. So if you take an interval which is just before the T0, both the both the algorithms are doing the same, have finished the same number of jobs. But for the greedy, the number of jobs completed will increase by 1 here, right? So in this interval, both of them have the same number of jobs, and at this position, the number of jobs of greedy will increase by 1 because it's completing a job here. So if you just look at an interval just before this, right, the number of jobs for after this finishes, the number of jobs for both of them is same. So before this time, the number of jobs for the because the number of jobs for greedy is increasing by 1, at this point of time the optimum should have completed more number of jobs than the greedy algorithm. But this is a contradiction to the fact that T0 is the first time when the number of jobs done by the optimum is more than the number of jobs done by the greedy algorithm. Okay, let's repeat. T0 is the time when the optimum is doing one more job than the greedy algorithm, right? So now that means that if you just look at the time just before T0, both of them are doing the same number of jobs. But if there is a job which is finishing right after the job that is under consideration, during this interval both of them are doing the same number of jobs, but at this point of time the number of jobs completed by the greedy will increase by 1. So if you just go to an interval just before this, the number of jobs for the greedy is 1 less than the number of jobs completed by the optimum solution. This is a contradiction to the fact that T0 is the first time when the optimum does more number of jobs than the greedy algorithm. So this particular job which is finished first cannot finish after the optimum has started this particular job. So the diagram should be, this is the job under consideration, greedy is doing something here, but the previous job that the greedy does should have completed before this, right? So this should have completed before this, right? This cannot continue till this is done. So now the greedy, because this particular job has already finished here, greedy picks the next job by looking at the among all the jobs it doesn't conflict. It has to pick a job which finishes first. So the greedy should have picked this particular job instead of this particular job, right? So since we are saying that, so that means that the greedy has made a mistake, right? So the greedy picks this one, not this one. So in that case, this last algorithm, this last job also cannot end before this, right? So it cannot end after this, it cannot end before this. If it ends after this, then what we are saying is that T0 will not be the first time when the number of jobs done by the optimum becomes greater than the number of jobs done by the greedy. But if you end this before the starting position of the last job done by the optimum algorithm, then the greedy should have picked this particular job instead of this, because this is the one which finishes first. So in both the cases we get contradiction. So this contradiction has happened because we assume that there exists a time T0 where the number of jobs done by the optimum is strictly greater than the number of jobs done by the greedy algorithm. So this cannot happen. So if you sort the jobs based on their finish times and assign it to machines and remove the jobs which conflicts with that and continue this process, what you get will be an optimum solution. So in order to implement this, you have to sort the jobs based on the finish times. So you need to know all the jobs well in advance, and sorting takes and log n time. After that, so what you do is that you consider the jobs one by one. You pick a job, you keep going to the next job. If the starting position of the jobs that you're going to consider is smaller than the finish time of the job that I just picked, then you have to ignore all these jobs. First time when you see a job which starting position is greater than the job that you just picked, then you can pick the job and continue this algorithm. So this algorithm can be implemented in order n log n time. In this video, we considered a specific problem and looked at several greedy algorithms. Most of them failed to compute the optimally, and we have seen that one of them is correct. But proving that the one which is correct is actually correct requires more effort. We have seen one such proof. Right? We'll come back to more generalization of the problem that we considered in the next video.